Okay, uh, we continue on our lecture within the Laplace transformation. And as we discussed before, that we have some examples how to use Laplace, and uh, since we are also discussed on how Laplace can be shifted, can be translated, we move Laplace in horizontal axis, and it will change its s. Okay, it's s from s to s minus a, right? So we can also use that for our Laplace transformation, especially for differential equations. So we can solve differential equations by transform all the differentials into Laplacian. So Laplace transform, and then we solve for the capital Y or the capital function that you want to solve. And then after that, after rearrangement, you go for the inverse and revert back to the original variables, right? The original variables, which is usually we are using t. As we can see here, that we have this, we transform with Laplace, we rearrange the functions, the transform function, and then we transform back using inverse. Okay, and then when you dealing with the inverse, you notice that if there is some form that need to be, maybe it was shifted, then you need um, to find out what is the uh, function that is shifted. Okay, and then you go and check with uh, maybe with your table. You make your table for some Laplace, and then you get the results. Okay. Same way with the second example. You have here solving through some little bit messy here. It's using a partial fractions, and then we get that all the constant, and we put in our system here, and we get the final results. And we inverse the Laplace, and we get the results. That will be our solution. So using Laplace, you will get more precise, direct answers, okay, rather than predictions using some of the methods that being used in the higher order, or maybe in the first order also. Okay, and I just want to know, yeah, this is from the quiz one. So I think I also agree. I need to make the time extend, so I need to make the time extended, and this is to make sure that when you have longer time, you can work most of the questions, right? So if the time is longer, I can work on all questions. So which means that sometimes longer or shorter, it doesn't really matter if you don't understand the question, right? But somehow, if you are working on a question, but you need to write like really long computations, then it means that you need longer time to solve it. But if the question itself too difficult, then you need to understand first the question, okay, before trying to compute. Okay. If you have any more feedbacks, okay, we can have in the last sessions later. If you have more feedbacks on how we can proceed with the quiz, because I think that the problem now is we are dealing with uh, exam using online system, and I tried my best to provide the system that you can just click and then provide. Uh, if you are just looking for, uh, like for example, if we have an offline class, I could easily just give you the paper, the questions, and you can write the answers. I think it's more flexible because you can write longer type of answers, right? And then you can just write the equation itself. But since it's online and I want to make sure that the answer that you type in is exactly the one that we are looking for, so I need to provide you with some sort of uh, like completions answers, like you need to solve some constant that you can try to work on, okay, and then maybe some multiple choices, and then true false questions. That's the best way that I can provide for our online approach. Okay, I think that's just my uh, announcement, a little bit announcement about what's next for quiz or maybe exam. Okay, and also this is also true for the next midterm, which is in Friday. So Friday, don't forget, we have midterm. So I hope everyone can join. Okay, so we will have a midterm. The durations is probably 2 hour, maybe 20 minutes, 2 hour 20 minutes, or almost 3 hours, or maybe two hour 15 minutes, and you can work your midterm. So we will have our uh, meeting using WebEx, and I will give you the link. You can click the link, and as usual, after finishing the exam, send me your PDF file, okay, your computation file, and I will also consider your file to be graded as well, okay, and then to match your writing with your final conclusions. Okay. That's around what we will do this week. Okay, going forward, what I want you uh, to work on within this afternoon session is we still have the translation theorem, okay, but now we are looking for the translation in terms of unit step function. And what is unit step function? Let me just write here. So translation on a t-axis. So before we are shifted our s. Let me maybe make it more clear what is really happening this one. So this is translation on s-axis. So we shifted the s, okay, from s to s minus a, shifted to the right, and now we are looking at the translation on t-axis, which means the t in the original functions that before we transform with Laplace. Okay. So first is the idea of unit step function. We call also this is Heaviside function. Okay. So what is Heaviside function or unit step function? Usually we write the unit step functions. The symbols is like u but with some curve. So usually we can write like that. This is unit step function, or some textbook you can check. They're usually using h. So this is unit step function, or the basic idea for this unit step function. So the definitions is if you have unit step function u t minus a defined to be 0, 1 for 0 to a, and this is from a forwards. Okay. So what's the deal with this function? What the function tells us is the functions will be valued as 0 from this interval from 0 to a, and this is going to be 1 for a to infinity. Okay. So what's the implication of this 0 and 1 is if you consider your electrical device, or maybe your lamp, when you click on and off, let's say this is uh, your lamp. Okay, when you click on, there will be light from your lamp, right? When you click off, it will be switched off. Okay, so basically that is what this function is. So you will be directly have value and directly disappear. And for the applications, the Heaviside is precisely useful in electrical engineering. Okay, useful in electrical engineering. So in our engineering world, a functions that are either off and on will be very useful for some cases. Okay? We need to be suddenly on and suddenly off. It will be really useful for our engineering structure. Okay, so yeah, we can try to imagine in a graph that if this is our Heaviside functions, let's say this is the t-axis, and let's say we have a in that way. So this will be valued as 0, and this will be valued as 1. Okay, that's our graph of our unit function, our unit step function. Sorry. And this is the definitions for the unit step. So it will be equal 0 from 0 to a, and it will be equal 1 for t greater or equal a. Okay, now what has happened when so if f defined for positive, for t positive, let's get this to be multiplied with the Heaviside functions t minus a. So what will happen? Okay, let's say we have a functions 2t minus 3. Let's multiply this with the Heaviside t minus 1. Let's say t minus 1. What will happen? We are going to have, I think I just can go for some, let me just write through the graph first. Okay, it will be 0 from this point forwards. This will be 0 up until this is t equal 1. This making 0, right? And from t equal 1 upwards, it will be going to be 2t minus 3. Or let me just write like that. Probably around that point, according to the linear equations, 2t minus 3. So this will be functions that is defined by this. So it will be directly turned off at this t equal 1. So there will be a portion of the graph that is turned off. So the turn off portions, also turn off from the interval 0 to less 1. Okay, or let me just plug in the graph. So if we see from this one, okay, so this is the definition. So this is the definition of Heaviside or unit step functions, and this will be if you have some function 2t minus 3 multiply with this Heaviside. Notice that this is turned off, right? This is turned off on some interval from 0 to 1. And then consider that from this part here, the last one, consider this is consider the interval that is from 0 to 2, and then from 2 to 3, and from 3 onwards. And this is correspond with from what we have in, if we try to make the unit step functions from 0 to 2 and 2 to 3, so we will have t minus 2, okay, and then this is t minus 3, okay, from what we have. Okay. Okay. So this function here, okay, when we have 2 minus 3, so if we see this graph, we can define this 2 minus 3 Heaviside t minus 2. So this is 2, this is 3. Okay. 2 minus 3 Heaviside t minus 2 plus Heaviside t minus 3. Okay, so this one is practically say that this will be 0 after 3. So it will be 0, turn off. Okay. And 2 minus 3 here means that it may result in -1 at some point. And this can be made 0, which means it's just equal to. Okay. So I hope you get the idea behind all of this. Okay. So why we have 2 minus 3 at this particular functions? Why is 2 minus 3? So Heaviside t minus 2 means that at this point 2, it can have 1 and 0, right? It can have 1 and 0. So when it is 1, when it is 1, so we will have 2 minus 3, which is -1. This is when this is equal 1, okay? And this when the Heaviside is 0, okay? And when this is when it t minus 3, so well we have, I think we can, let me just erase this. to make it easier to follow. Oh, I think I need to just erase that. Okay. And then write that ut minus 2 and then ut minus 3. So this is 0 and this is 1, right? And this will be the Heaviside when it is equal to 1. Right, let me check. So 1, 2 minus 3, it's minus 1, right? Minus 1 plus 1 is 0, so it's 0. Okay, so it's 0. Okay, so this is how we can construct our Heaviside, and we can play with it. And then when we multiply, we can multiply and then write down that at some certain point it will turn off. It will be just a 0 value. Okay. So generally, we can write system. So generally, we can write that the functions, we can say that this is equal to g and h for some several interval from 0 to a, and then from a onwards. Okay. When we write this, this is the same as minus g of t Heaviside from t minus a, and then make it smaller, and then plus h of t Heaviside t minus a. Okay. And then if we also have similarly, so let me write here. Similarly, if we take if we have more than 2 possibility, let's say 0, we can also write and then Heaviside and then t minus a and minus t minus b. Okay, to make sure that we can have more variations and we can at least write the piecewise functions as a Heaviside. We can try. So for example, let's say we have this. So this we can write as our correlations here, which we have 20t. So f of t, we can write 20t minus it's gt, okay, gt the same thing, 20t, and then Heaviside function of, we are only having t5 here, so t minus 5. Okay. So basically what we have is precisely this graph here. Okay. So this is 20t up until 5, because at 5 it has the Heaviside, so it's switch off. So it switch off and take the zero value. Take the zero value. So switch off. Switch off from 5. Okay, so that's how the Heaviside function becomes useful, because it can zeroing the value and switch off the graph and make it zero value. And why this becomes important? Because in some way we can also make another theorem for translation using this Heaviside. Okay, maybe you need to take some time to rewrite this, and maybe some time to think. Okay, so maybe let me give you a couple of minutes. Okay. Okay. So let me just go through. Let's consider general functions. Okay, consider general function. This will be defined for this positive. So the piecewise defined function. So piecewise defined function. This will be f t minus a, Heaviside t minus a. It's either 0 or f t minus a, because Heaviside makes it 0 or 1. Right? This is for interval 0 to a, because at a shifted, right? It means it's going from 1 to 0 or 0 to 1. And then it's equal t minus a when t is equal a or greater than a. Okay. In this figure, if you look at what will happen here when we adding the Heaviside functions, if you clearly see what we are going to write, okay, according to this notations here, this piecewise, from 0 to a, the value will be 0. The function will be 0. So this is 0, right? So its value will be 0, and then at a it will be shifted to 1, right? From 0 to 1, and this will be the graph. So this will be the f t minus a graph, right? But when you compare with the original functions that you have, just let's say just f of t when t positive, okay, just like this. But when you try to make out with these Heaviside functions, it seems that we know that there will be some sort of shifted a, right? It seems that it's kind of shifted from the original function f of t, right? So it seems that f of t shifted a units, right? And becomes okay. In the previous, so recall, in the previous theorem, the exponential multiple of ft, it will result in translation of f of s, or we know that e with power of a 8 at of f of t, this will be results in translations of the capital F on the s-axis, right? So whenever f of s is multiplied by an exponential function, the inverse will be shifted, okay, along the t-axis. So implication, f of s multiplied. So if f of s is multiplied by e with power of negative, let me write in green. Inverse transform of product e f of s is the function f small f shifted along the axis. As we can see from the graph here, it's shifted a units, right? This is what we call the second translation theorem, or second shifting theorem. So basically what you have, if this is Laplace of functions, and let's say a is positive, then Laplace of f t minus a, and then Heaviside t minus a, this will be equal to e negative as f s. Okay, we'll write some proof of this theorem, but that will be next page. But let me just give you this. Okay, this is the second translation theorem. Okay. So basically, what can we deal with this is basically it's just how we visualize the functions. going shifted. If we take the Heaviside, if we multiply the function with Heaviside and make this into ft minus a, Heaviside t minus a, this is what will happen. Okay, and it is just to give you some notions about if we multiply the capital F with some e with power of negative a, the inverse transform of the product is the original functions that is shifted on the axis. Okay. Okay, let me give you some computations on how we are going to see this Laplace in terms of our computation in integral. Okay, so for the Laplace, okay, the idea is integration from 0 to infinity. Let me just write all things here. Okay, so first we are going to consider this Heaviside with our interval. So we will have the interval 0 to a, 0 to a, and a to infinity. So we will divide this integral becomes two separate integrals. So first, from 0 to a, and plus a to y100. It should be infinity. Okay, sorry. And then f t minus a, Heaviside t minus a dt. Okay, remember in the Heaviside, from 0 to a, this will be equal to 0. From t greater a, this will be equal to 1. So what will happen here? This will be 0 for this interval. Maybe to make it sure, this Heaviside. So this is 1 for t is greater or equal a. Okay, now this is resulting in a to infinity okay. Okay, maybe write with some substitutions to make it easier to calculate. Maybe let v is t minus a. So dv is equal to dt. So we are going to have, so Laplace of f t minus a, Heaviside t minus a. This will be equal to a becomes 0 because we substitute with v, and infinite still infinite. E negative s. This will be v plus a, and then f v, and then dv. Okay, we have this will be e negative sv and e negative as. Okay, the variable is v, so the other one is constant, so we can factor out negative as. what will happen here is this is basically say that this is Laplace of f t, right? Or fv if you want, but still the same. So it's v, just change the t. It's just precisely the same as what we are going to prove. That is, the Laplace will be the capital F. Okay, so this is capital F, right? So Laplace of f t minus a and Heaviside t minus a equal to e with power of negative as multiplied with the capital Fs. Okay. Okay, now if we identify, okay, so if we want to identify, let's say we have f of t is just 1, then f t minus a also 1, okay, and f of s Laplace of 1 is 1 over s, right? So Laplace of the Heaviside, only the Heaviside, this will be e negative as divided by s. Okay. This is if we want to set the f of t as a constant, so we just need to divide by s. Okay, and then when we have, like for example, the previous equations that we have, 2 minus 3 Heaviside t minus 2 plus Heaviside t minus 3. This is the figure, I think, yeah, the last figure. Let me just crop. Okay, so we can write down, if we want to Laplace this, so this will be 2 over s, negative 3, or maybe, let me write one by one. So Laplace 2 Laplace of 1 minus 3 Laplace of the Heaviside, and then plus Laplace of Heaviside t minus 3. Okay. This will be 2 over s. This will be negative 3, and then the Heaviside using this e, so e with power of negative as, or now a is 2, so we can write this negative 2s, and then over s. Same thing here. This will be e negative 3s over s. Okay. This will be the Laplace of this function. So now we have the Laplace of the Heaviside. Okay, Laplace of Heaviside. So when I put some symbols like u, but it's not really u, it's more curvier, it means that it's the Heaviside. Okay. And then also we have the inverse of this. Okay, the inverse of this. Let me give you the next page. Let me take some time for you to write or to think. Okay. Okay, let me give you another theorem. Okay, so the inverse form. Okay. So if, let me just write that f of t is Laplace inverse of the capital Fs. Okay. Then the inverse with a or maybe just and a is positive, then the inverse Laplace inverse equal f t minus a, Heaviside t minus a. It just reverse the previous one, right? Okay. No other term introduced, so just reverse the inverse. So if we take some example, so if we want to Laplace inverse 1 over s minus 4 and then e negative 2s. So what will happen here is this is e negative as, right? And this is f of s, right? So we will have first is this is f t minus a. Okay. So let's inverse this 1 over s minus 4. It's become e, right? So let's identify. Maybe a is 2, f of s is 1 over s minus 4, and then the Laplace inverse of f of s is e with power of 4t. Okay, so we need to so this is f of s, so or maybe we write f of t is this, so f t minus a is, or t minus 2 now, we write t minus 2 is e 4, and then t will be changed to t minus 2. Okay, that's the first one. So 1 over s minus 4 becomes e 4 t minus 2, and then e with power of negative as. This will be our Heaviside. So we write Heaviside t minus 2. Okay. I hope you get the steps. Okay, you get the steps. Another one. Let's try Laplace inverse of s over s squared plus 9. E with power of negative pi over 2s. Again, we start with f of s is this. Okay. So we can write that f of t is Laplace inverse of s squared plus 9, which is the cosine, right? So cosine, the beta is 3t, right? So f, and then we know that a is pi over 2, right? So f t minus pi over 2 will be cos 3 t minus pi over 2, like that. So we can write down, so this become cos 3 multiply t minus pi over 2, and then Heaviside t minus pi over 2. Okay. Okay. Got it? Is it clear how to transform this Heaviside? Or still confusing? Okay. Yeah, the idea is, I think you need to understand first the Heaviside and the Heaviside function. And remember that just alternate answer. So cos 3 t minus pi over 2 we can transform to sine, right? With because it's pi over 2 addition and subtraction, we can transform to sine 3t, right? Using the formula for cosine. Okay. And there will be also alternative theorems by using some substitutions to help you rewrite the forms clearly. Okay. Let me give you another example also. But let me just give you this for a while, okay? For taking notes. Yeah, let me give you a couple of minutes. Okay. Okay. Because in the Heaviside, we always have the t minus a, Heaviside t minus a, and we can Laplace inverse, and then we can find the Laplace itself. If we want to find, for example, if we want to find Laplace of t squared Heaviside t minus 2. It seems that this t squared, we need to force out this to make it f t minus 2, right? So if this, let's say the t squared, we need to make it into t minus 2 squared. Okay, let me just give you the deal with this. And then we need to make sure that this is becoming t squared, so we need to plus minus with some function. So plus plus 2t minus 2, or this t minus 2, we can make it again, we can make it into t minus 2 like that. Okay, but of course we are going to have another, let me just write 4 with that. Okay, so 4t minus 2, so it will be going to have plus 4. Okay. So we are going to have this as our t, or our functions. Okay, so t minus 2, this is 4, sorry, 4, so t squared minus minus 4 minus 4t plus 4 plus 4t minus 8 plus 4. So okay, it's true that this is equal to t squared. So we can use this to take the Laplace, okay, that we can rewrite the t squared with this function. So we are having Laplace of the t minus 2 squared and then plus 4 t minus 2 and then Heaviside t minus 2 and then plus 4 Heaviside t minus 2. The first one here will become 2e negative 2s, because a is 2, right? A is 2, and then divide with s cubed. S cubed is from, remember, the t squared. So Laplace of t squared is 2 factorial divided with s cubed. So 2 factorial is 2, so it's why it's 2 here, right? Okay, and then e with negative 2s is from the Heaviside. And then plus 4t minus 2 is just 4 divided with s squared is just t, and then t minus 2 Heaviside is e negative 2s. And then plus 4 e negative 2s. This will be defined just by that. Okay, but the problem here, okay, it's not that we don't get the correct answer. It is correct answer, but it's time consuming. It's really long, right? It's really long to compute this. So how about if we define, okay, if we define so alternative solution. Let's just write Laplace. Let's say we have g of t and then Heaviside t minus a. By using the same structure in integral, we can take these integrations a infinity from the same structure we have here. Let's just change this f t minus a with our new function g. Okay. So e negative s t g of t dt. Okay. Now we can say that this is precisely 0 infinity e negative s, and take these substitutions and let substitution u is t minus a. Okay. So t is u plus a. Okay. Now we get that t becomes u plus a, and then this is also u plus a, and then dt is equal to du. Okay, so this is becomes du. That we can finally say that the Laplace of g of t, Heaviside t minus a, is equal e negative s or negative as and Laplace of g t plus a. So we can write an alternative Laplace form with this Laplace. Okay. Or to be more clear, what I mean here is we can have this as, and then we are having this negative s u gu plus a du. This is the same thing as what we have before, right? This is the Laplace, right? Laplace. So we can take this as our approach. So if we are having, for example, if we are going to write down this function here, the Laplace of the t squared and then Heaviside t minus 2. What we can do here is we define that a is negative, a is 2, sorry, and then the g is t squared. So basically what we are going to do is it's e negative 2s and then Laplace of g, and then this is t and then plus 2. Okay, or we can say directly that this is Laplace of the g is t squared, so this will be t plus 2 squared. Or we can say that this is t squared plus 4t plus 4, right? So we can write Laplace of t squared is t squared becomes 2 over s squared. Oh, sorry, cube, sorry. It's supposed to be cube. Plus 4 over s s squared. Sorry. This is 4 over s. And then this is equal to what we have here, right? This is equal. Okay. So we can take substitution and make a new form that is, if you want to make gt Heaviside t minus a or f of t Heaviside t minus a, we can do that as well, and we can make it into our t plus a like that. Okay. Any question? Okay, any questions? I think my assumption, okay, my assumption for your study and learning for this Laplace, I think the very beginning, the Laplace and its inverse, I think it's very easy to comprehend, right? It's not too difficult, although you need to familiar for what Laplace is. But again, when we deal with a differential equation, and now we deal with the Heaviside functions, I believe it's simply a little bit becomes heavy subject. Okay? So my suggestion is, to get through the Laplace, inverse, and differential equations, you need to know at least the very specific steps, the very basic steps to solve using Laplace. Okay, that's the first one. The second one, you can try to look on what is Heaviside. Okay, Heaviside means. Let me check my sticker here. Okay, maybe this is what will happen with you. Okay, the next sections is just I think some examples and some examples. Okay, I'll give you two examples before another happy subject again. So we have translation, we have the Heaviside functions, and then we have some, we call this additional operational property for Laplace. And we call the next sections one term. It's called the convolutions. It's a little bit complicated. Let's try slowly. Okay, let's go to the next page. Okay, evaluate Laplace of cosine t and then Heaviside t minus pi. Okay. Again, the first thing, identify. Okay. To identify, this will be our function g. This will be having, it should be like t minus a, so we can identify a is pi. Okay. So at least you can write that is supposed to be equal to, well, the first is going to be having e with power of something a, right? But let me just write, if g of t is our cosine t, a is pi, then because we need to have g t plus pi, right? We are going to have cosine t plus pi, right? Cosine t plus pi, according to our trigonometric, this will be negative, right? I hope you still remember the very basic trigonometric like this. Okay. Y is negative. You should be aware of that. The quadrant things. One, 2, 3, 4. Cosine in 1 and 4 is positive, and this is not in 1 and 4. Hope still remember that. Okay. Okay, and then Laplace this will gives because it has negative, so we'll write negative at the front. E and then as it's pi s negative, okay. And then Laplace Laplace of cosine t, okay. And this will be turns out to be cosine t is, let me write, negative s squared plus 1 e negative s or maybe pi s, like that. Okay, and then finish. Okay, another example. Solve the differential equation y prime plus y equal f of t, where y0 is 5 and f of t, okay, we have the Heaviside 0 and then 3 cosine t. This is for 0 to pi, and then this will t greater than pi. So we are having the Heaviside. Okay. So first, what can be written within this Heaviside? Okay. Practically, we can write this as, this is the original when we have this 1, right? When we have 1. So we write this 3 cos t, and look at this, we have the a is pi, right? So we can write the Heaviside and then t minus pi, okay? And that's our function, okay? Now we need to Laplace all the differential equations. So let me write the differential equations become 3 cosine t Heaviside t minus pi. So Laplace y prime plus Laplace of y, and 3 Laplace of cos t Heaviside t minus pi, okay. And then as usual we get s and then minus y0 of, I forgot to mention what else should we have? Y0. Oh, I think we already have all. So plus s equal cos t is s over s squared plus 1, right? So let me write negative 3 s squared plus 1. This is from the previous one here. So we just rewrite one more. And then e negative pi s. Okay, what else we need to take? We need to group this. Y0 is 5. So this is 5, negative 5. So we will have 5 minus 3s divided with s squared plus 1 e negative pi over s. And then the ys is 5 over s plus 1. And then we need to take the partial fractions, and then this is, I think, considerably a little bit complicated. Okay, so we have from this 3s over s squared plus 1. Three s, so s plus 1, s squared plus 1. Okay, so we will have, let me use this. So s plus 1 plus s squared plus 1. This is a, this is b, s plus c. Okay. Okay. So a s squared plus 1 plus b s plus c s plus 1 is equal to 3s. So as squared plus a plus bs squared plus cs plus bs plus c equal 3s. So a plus bs squared plus b plus c s plus a plus c. Okay, a plus b is 0. B plus c is 3. A plus c is 0. Okay, so we can start with b is 3 minus c. So a plus 3 minus c is 0, and a plus c is 0. So we can have some sort of subtractions. So 3 minus c minus c. So 3 minus 2c is 0. So c is uh, 3. So c is 3 over 2. 3 over 2. C is 3 over 2. Then b plus 3 over 2 is equal to 3. Or 6 over 2 to make it easy. This is also 3 over 2. Okay, good. Maybe it's 3 over 2. So a is negative 3 over 2. Okay. Okay, let me continue in the next page. So let me write the conclusions. This is 5 over s plus 1 minus, because all is 3 over 2, I will factor out 3 over 2. The first one is negative, right? Negative s plus 1. E, don't forget we still have e in all components. This is s squared plus 1 plus s squared plus 1. Okay. Okay. And then we can inverse. And then do Laplace inverse. So Laplace inverse of 1 over, let me write first, this will be 1 over s plus 1 and e to the power of negative pi s this is going to be negative t minus pi, right? And then Heaviside t minus pi. Okay. Remember that we have s minus minus a, right? So we have minus, and then we have pi as a shifted units, so t minus pi and minus. And then we also have another term, Laplace inverse of 1 over s squared plus 1 e negative pi s. Okay, every time you have x squared plus something, it's either sine or cosine. But in this time, because the top equation is a constant, so it should be sine. So it should be sine. The shifted one, the a is pi, so sine t minus pi. And then the Heaviside t minus pi. Okay. And then lastly, we have s squared plus 1, similar with sine, but this is cosine for now. So cosine t minus pi and Heaviside t minus pi. Okay, so the inverse of this whole thing here, so let me go through here. So the inverse of, or the solution is 5e with power of negative t. It's just directly from 5 over s plus 1. And then plus 3 over 2 e negative t minus pi. And then the Heaviside t minus pi. And then negative 3 over 2 sine t minus pi. Heaviside t minus pi. And minus 3 over 2 cosine t minus pi, and then Heaviside t minus pi. Okay. We can write in more clear and maybe take this 3 over 2 going outside. And then we can take some trigonometric values for sine t minus pi and cos t minus pi. For sines become positive, right? If you have negative sine, t minus pi it's become positive, right? It's multiplied with the negative, so we will have plus. So plus sine t plus cos t and Heaviside t minus pi. Okay. So we will have, this will be 5e negative t and 5e negative t plus 3 over 2 e negative t minus pi plus 3 over 2 sine t plus 3 over 2 cos t. This if we have, so it is for value 0 for the Heaviside, so we have 0 to pi, and this will be for t greater equal. Okay. Okay, any questions? Any questions? Okay, probably we'll have a short break, maybe 5 minutes break, or maybe 10 minutes break if you want. Maybe 5 minutes break, short breaks. Okay. Okay, we continue, and the next part is we will have another sections. And we are going through. So after the Heaviside functions, we are going to look on some of the additional operational properties. So this will be so additional operational properties. Okay, the first one, we'll have derivatives of transform. Okay, remember that recall. Okay, let me write recall that the Laplace of function of t is a capital F s, right? Okay. Then if we try to write from the capital F like this and take the derivative ddx, okay, this will result in, so take the ddx at the front. The f of s is the Laplace, right? So we can say that, let me write one by one. So Laplace of the f of t, right? The Laplace itself is the integrations from 0 to infinity of e negative st ft dt, right? And then, if you're looking here, we can write this, and let me write with Leibniz notations, because we have s and t inside. So e negative st ft dt. Okay. Now we differentiate with respect to s. So we will have this will be negative e negative st. Okay. tst, sorry. So we can write this, and let me put negative outside here. Integration from 0 to infinity, and this will be test, but let me write e negative st and then t, okay, and then f t dt. We can say that this is equal to Laplace of the function become tft, so tft. Okay, so conclusion here, the Laplace of tft, let me write tft is negative dds of Laplace ft. We write to make sure that we are on this. So dds Laplace ft. Okay. Okay. So from here, from this, we can write similarly if we have t squared ft. Okay, let me write it more clear in the new page, but let me just wait for a moment so that you can maybe take notes and maybe think on this all this process. Okay. Okay. Now, if we take Laplace, let's say we have t squared ft. This Laplace becomes t multiplied with t ft, right? And we can say that this is negative TdS of Laplace t ft, right? Or we could say that this is negative TdS and then negative TdS again for t ft, and then Laplace of ft. And then this will be positive the second derivative of Laplace f of t, like that. Or maybe to make sure that we are on the same page, let me write the last conclusions that will, the last conclusions is okay. So basically what we are doing here, so this so the subjects will be having t and then function. So this is t, right? And this is, let's say this is g, function g. So the function g becomes the Laplace. So the t ft is dds Laplace ft, right? So dds, this is, let's say gt, but gt is another having another tft. So tft is having another derivative of ft. So derivative, so it's twice derivative, so second derivative. Okay, now we can suggest that what will happen if we have t with power of n, not power, sorry, it's derivative. So if we have the derivative, well, it's power, but later it will be the derivative, sorry. So t n ft, like that. So this will be equal, base what we have. If we have the first derivative, it has negative, right? When we have the second derivative, it has negative, negative become positive. So whenever we have a power that is odd, like 1, 3, 5, it will have the negative. It will have, if we have the even, like the squared, 4, 6, and so on, we will have a positive. Okay, so this will be equal to negative 1 with power of n, and then how many the derivative will have will be also depends on how many n it is. Okay, so this is if the capital S, capital F S is equal Laplace of ft, and n is start from 1, 2, 3, and so on. Okay. So the more power you have on the t, it's basically saying that how many times you will derive. Okay. Now, example. If you want to evaluate, if you want to evaluate t sine kt, let's say we have. So we have this is f of t, let's say sine kt. So the Laplace, okay, Laplace of f of t. Remember we have k over s squared plus beta squared is k, so k squared like that. Okay. Okay, now we are going to use this t sine kt. So we will have negative dds of Laplace of sine kt. So negative dds of k s squared plus k squared. So what will happen now is we are going to differentiate with respect to s. So we are just focusing on differentiating this bottom side. So we are going to get this into -1 there and -1, and then we are going to have a negative in the front, and it will be a positive because of the negative dds. So we will have s squared plus k squared squared from -2 to we can put down again, and then we can have k multiplied with s squared derivatives, it becomes 2s, so 2ks. Okay. Okay, I think you can derive it normally, just like usual derivatives. But now we can have options to solve the Laplace or to find the Laplace transformation. We can use the translations like we did before, or we can use this derivatives theorem. The result is the same. Okay, let me just show you. Okay, let me just show you. Okay, now if we going through t e with power of 3t, we can say that this is actually our Laplace, our Laplace, okay. Laplace of t when s is going to be shifted to s minus 3. Remember that this is important here, that we need to see this 3 as our a, right? So we are going to have Laplace of t is just 1 over s squared, and then we are going to shift it, this s, into s minus 3 squared, right? If we are going to use the derivative one, we can also do that as well. Remember that this is negative dds of Laplace e 3t. Laplace e with power of 3t is 1 over s minus a, remember, so it's 1 over s minus 3. So negative dds, this is 1 over s minus 3. And as usual, this will brings you to s minus 3 with power of -1, bring to the front negative, it's become positive. -1 is become -2. So it will be my s -3, or so you can choose whichever method you want. Okay, you can use the translations, you can use the derivative one, same answer. Okay, any questions? Okay, any questions, everyone? Perhaps on Wednesday we can have, I think, summary, right? We can have summary. Okay, because if you miss out some of it at the middle, from middle to the end of the Laplace, it will be difficult. It will be difficult if you miss out some parts in the middle. Okay. Okay, let me just give you another differential equations. Okay, if we have, so solve, let's say x double prime plus 16x equal cos 40. So this is using x with a variable of t. So we have initial conditions. Okay. Okay, now we can say that we are going to take Laplace. So let's say we have Laplace okay, Laplace x double prime. This is s squared minus okay, and then plus 16. Sorry, it's not y, it would be x. Okay. And then x s, and then this will be s over s squared plus 16. This will be 0, this will be 1. So x s squared plus 16 is equal to 1 plus s. Okay. And then we can take the equations. Squared that. Okay, from the previous example, which one is that here? Oh, from here, we know that if we have Laplace of t sine kt, it will be 2ks over s squared plus k squared squared. Okay, remember we have this similar structure, right? So we can use that also. Then we can write down that if we have let the inverse of the 2ks over s squared plus k squared squared, this will be t sine kt. Okay. Now, to make it true, now if we want to take the inverse, so let's take inverse of this transform equation. Now we will need to have 1 over 4, or let me write with green color. We need to transform back to t. Let's say this is s squared plus 16. Okay, so we have 1. So to make sure that we are able to transform this back, so when we have this x squared plus 16 squared, we need to have 4s, right? 4s. Then this will be t sine 4t, right? But for the first one here, this is just 1, right? So this is just 4, okay? And plus the next one we need to have is, well, it's not 4, should be 8, because 2 with 4 is 8. Sorry. So the next one is 1 over 8. 1 over 8 of the Laplace inverse. This is 8s, or using 8s, s squared plus 16 squared. This part will be 1 over 4 sine 4t plus 1 over 8. This will be going to be t sine 4t. And that's our solution. Okay. 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 Let me just give you time for writing. Okay, because after this, we move to another additional operational property. We call the next sections is the convolution. Okay, convolution. Okay. Okay. Let me move to the convolution. Before we learn more about what convolution, or we define what convolution is, let me just recall some important notes. Okay, recall that in Laplace transform we have linearity, right? Linearity of Laplace. Okay, so if we have Laplace f of t plus g of t, we can simply Laplace each of this f and g, right? So we Laplace f of t and Laplace of g of t, right? This is linear. But if we have Laplace, what will happen? This is not the same, let me write here. This is not the same as Laplace ft and Laplace g of t. Okay, this is not the same. So so for this Laplace linearity to make sense is, remember that every time you take Laplace transforms, you're actually integrating. Okay, you're actually integrating. So remember the property of integral. Okay, so if you have f of t plus g of t dt, you can separate this integral easily, nicely, right? And that's what we do with the Laplace. Laplace is type of improper integral that takes that when we are using it, we can simply change some of the differential equations become an algebraic. Some say that we can make it into algebraic, and then we can then solve for rearrangement, and then we can take the inverse and put back the functions as it is. Okay. But how we can approach this problem here? This is a problem in our Laplace, because if we can do something here, if we can approach with some type of multiplications, we can have um, our computation much more useful, right? Then we need some types of product in this Laplace. That type of product is called convolution. Okay, so we can make this Laplace f of t. We say it's convoluted with g of t. So it's like a star like this. We call this a convolution. And one of the convolution property is we are going to multiply these two. These two Laplace of f of t and Laplace of g of t. And we say that this is Laplace convoluted between f and g. Okay? And now we can try to define what is convolution. Okay, so definitions. A convolutions, let's say convolution like that, or f of t, g of t convoluted is equal, take integrations. I will reuse the same. Let me check the textbook. Let me check it. I will need to use the same. Okay, I think the same. So 0 to t of f, we are going to introduce new variables. Not new variables, it's just dummy variable to make this useful. So it's tau, okay, and then g t minus tau, and d tau. We can also write the convolution as f convoluted gt, just like your product rule, similar, but it's this different definition, of course. But because with integrating this whole function with respect to tau, and we are going to evaluate with the t variables, we can say that the whole thing here, the integral, is actually a function of t. So this is a function of t. Okay. So, for example, before we prove why this is true, and I don't think we have time, but let me just write first. Okay. So if we want to write e with power of t and convolute it with sine t, this is basically 0 to t, e with power of tau, our dummy variable, and then sine t minus tau, and the tau. Okay, then what will happen? Okay, I think we can solve this by integrating by parts. And I will just skip some formulation. Let me just write this becomes e with power of tau sine t minus tau plus e with power of tau cosine t minus tau. All will be evaluated from 0 to t. And the result is half negative sine t negative cos t plus e with power of t. Okay, now this will be, if we want to find the Laplace e with power of t convoluted with sine t, then we can say negative half Laplace of sine t, negative half Laplace of cos t, and plus half Laplace of Laplace of e with power of t, which is, we can write down this is 1 s squared plus 1 minus half, this is s squared plus 1 plus half and then 1 over s minus 1, right? And then we can say s minus 1 and s squared plus 1. We can solve this and you will see that this will be 1. We can try, if we would like to go from sine t convoluted with e power of t, we will have the same results if we are doing sine t convoluted with e power t. So one property that will be important in convolution is if we convoluted f convoluted g, it's equal g convoluted f. Okay. I'll write some property for you so you can just stick to this summary. Okay. So some property, let me write ft convoluted g of t is equal 0 t f tau gt minus tau d tau. And then property is equal g of t convoluted f of t. And also if you have f, let me write with just f convoluted with g convoluted with h, this will be equal to f convoluted g convoluted h. So no matter which part you are working first, it should be, the result at the end should be the same. And also if you have g plus, okay, h, we can write f convoluted g plus f convoluted h. Okay. Well, if you would like to show just one property to prove on, that if we have f t convoluted g of t, this is from 0 to t, this is f tau g t minus tau d tau, right? To prove this, we can set some substitution. Let's just substitute to change the t minus tau, okay? So that this will be one variable, complete variable. So t or tau is u minus tau is t minus u. So d tau is negative du. Okay, now we can exchange this and make it into negative. Now we have from, because we changed to u, so u is t minus tau, so this will be 0, so this will be t. Okay, and this part will be f t minus u, and then g of u du. This simply, just the same way, we just switch this t and then multiply with negative, and then this is precisely the same with our property. Or we can say that this is g of t convoluted with f of t. So it's the same result when you reverse the order. Okay. 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 Let me just close the session for afternoon sessions with some theorem. Okay, with one theorem here. We call the convolution theorem. So if f of t, not good, and g of t are piecewise continuous on 0 to infinity and of exponential order, then Laplace of f convoluted with g is equal to Laplace of f of t and Laplace of g of t, and simply we just write down capital F and capital G. Okay. I will just stop until here, I think, until the convolution theorem. And I think, let me check. Or maybe let me just take some time to prove. It just take me 5 minutes, 10 minutes, okay? So convolution theorem, to prove this, let's take some formal definitions. Okay. Let's take some formal definition of capital F. So let this becomes our integral. Just using formula for Laplace. And let's just use tau, okay, to make sure that all using the same dummy variable. And take the g of s also. Similar structure with f. And let's take with different dummy variable. Let's say we are using beta. Okay. And by taking the f multiplied with g, we simply take these two integrations Okay, we take these two integrations and remember we are having the 0, 0, infinity, right? The integration. And what interesting here is we can set up, let's say we are going to set up the this Laplace becomes double integrations, and then set up this e oh, this is s, sorry, this is negative sb. So we have negative s, this is not t, this is should be tau. So tau plus beta, and then f tau, and then f beta, and then d tau d beta. And then let's see from our perspective, we can set up this tau going to be here. I think we need to make this not f but g. Okay. And if we let t equal tau plus beta, and let's assume that tau is fixed for the beta one, so dt is d beta. So we can say that these multiplications will give f tau d tau, and this will be equal to, so let's exchange with 0, with beta 0, so t will be tau, so this is tau until infinity, and this is st, theta, tau plus beta, and then g, beta st minus tau. So since f and g are piecewise continuous and of exponential order, this is also possible to interchange the order of integration. So if we want, we can also interchange the order of integrations. And we can say that we can take this, okay, integrations from 0 to t. Oh, sorry, it's not 0 to t. And then dt. Okay. So we can say that this is Laplace, right? This is Laplace of this. This is f convoluted with g, right? So we can say that f s g s is Laplace of f convoluted with g. Okay. Okay, I will maybe review. We still need to discuss this. Okay. But let me just stop until here, and we're going to have another feedback. Okay, another feedback. Okay. So I hope you can join, and maybe before that, is there any questions? I know this Laplace becomes very tough now, but I hope you can follow up. And my suggestion is just to review your sessions, review the recording. We'll give you the recording on the Moodle. Okay, the link. I will give you the link on the Moodle. Okay, I will stop this sharing and let me go through the second screen. Okay. Another feedback. I just want to know what kind of feedback that you might have. And I need you to write with honesty. So if you feel that it seems lost or confused, well, please tell me. Okay. Let me just give you maybe the short version of what you need to learn. Okay? What you need to be focused on. Okay. Okay, I will start. Okay. Just two questions. Okay, just two questions. And don't forget to write your student ID. Okay. So let's start. Okay, remember the Laplace inverse. Okay, Laplace inverse. You can take your times to check your notes. I give you 2 minutes. I hope that is enough, sufficient. So you need to plus A, B, C, and D, plus all these four letters. And then forget that probably there will be a negative sign, right? Because of it has negative 1 over s plus 8, but in the right side it's just plus plus, right? So probably there will be a negative 1. Okay, how many times? Okay, 35. Okay, just to check your skill on Laplace. Okay, negative signs is, I think, important here. Will we change the results? Okay, good. Negative 1 is the answer. Okay. Okay, good. Okay, ready for the last question? Okay, you may use any method you want to check. You want to have any method, but my suggestion is just using Laplace. Using Laplace. First, use Laplace to transform the differential equation. Solve for the capital Y, and then inverse Laplace, and that will be your solution. And you need to check your solutions and plus all this A to F. Okay, 2 minutes. I hope it's sufficient. But maybe it's too short. Maybe it needs to be 4 minutes or 5. Okay, 1 minute. Okay, 3, 2, 1. Okay. Okay. Okay, congratulations. Okay, you win the game. And yeah, I hope everyone can enjoy the Laplace and Laplace Inverse at least. Uh, yeah, let me know your feedbacks. Anything that comes into your mind with Laplace, okay? Whether you think too difficult or maybe what else that we need to improve. Okay, any feedback you can also write. You can write more than one column. If there's nothing left for you to write, I will just stop until here. We still have time actually, but I'll just stop until here because the next part is we need to have refresh our minds, and I think we can just let it. We can just let's start the new sections on Wednesday. Okay. Okay, if there's nothing left, so I will just stop until here. And don't forget, we have the homework, the second homework that you need to work on before the midterm. So I hope everyone can work the homework. Okay. If you have any trouble, difficulty on the homework, please let me know. Okay, please let me know. Okay, so I think that's all for the afternoon session. We will continue on Wednesday. Uh, we will still in the convolutions, some example, and then maybe go to Dirac delta, and then that will be the last part of Laplace. Okay. I think for homework, it's okay if you just upload to the Drive folder. Okay. I think that's still okay but for I think for quiz and midterm later, then maybe it's going to be to the Drive folder is the different with the I think I will just give you the new link, okay, in the Moodle to let you know that you can just upload on that Drive folder. Okay. Okay, thank you all. So I will stop this recording.